A newly discovered super-Earth travels along a highly eccentric orbit that carries it both into and out of its star's habitable zone. The planet endures dramatic temperature shifts, extreme heat when near the star, and intense cold when far away. These rapid changes challenge traditional views of continuous habitability and prompt scientists to consider whether brief periods of moderate conditions might allow life to survive, perhaps with the aid of a thick atmosphere or subsurface reservoirs. Imagine a planet on a 650-day orbit that experiences scorching conditions during its close approach and freezing temperatures during its distant swing. Think of this planet as a roller coaster alternating between blazing heat and icy chills. Radial velocity techniques measure the tiny shifts in a star's motion caused by the gravitational pull of orbiting planets. With sensitivities reaching just a few centimeters per second, these measurements can reveal the presence of low-mass planets whose subtle gravitational tugs create only minimal wobbles in their host stars. A star's spectral lines shift ever so slightly due to a planet only a few times the mass of Earth orbiting it. It is like using an ultra-sensitive scale to detect the weight of a feather among much heavier objects. Advanced spectrographs such as espresso and HARPS split starlight into its component colors, allowing astronomers to detect minute spectral shifts caused by orbiting planets. Their remarkable stability and resolution make it possible to uncover low-mass planets that would otherwise remain hidden. Thousands of high-resolution spectra taken over many years reveal slight shifts that indicate the gravitational influence of unseen planets. This technology is like upgrading from a blurry camera to a high-definition one that captures every subtle detail of a moving subject. Stars naturally exhibit variations due to magnetic cycles, star spots, and flares, which can create signals similar to those produced by orbiting planets. By analyzing these variations, astronomers can distinguish between the noise generated by stellar activity and the genuine signals of planets. A star might show periodic brightness changes because of surface spots. Advanced techniques help separate these effects from a planet's gravitational signal. It is like using noise-canceling headphones to block out background chatter so that a soft, distant sound can be clearly heard. Gaussian process, GP, modeling is a statistical method used to represent and remove complex correlated noise from observational data. By modeling the quasi-periodic variations due to stellar activity, GP techniques help reveal the consistent periodic signals of orbiting planets. Applying a GP model can filter out irregular fluctuations from a star's magnetic cycle, exposing the steady signal of a hidden planet. It works like an advanced filter that removes static from a radio signal, allowing the true melody to emerge. The habitable zone is the region around a star where conditions may permit liquid water. For planets with eccentric orbits that only intermittently cross the habitable zone, the environment alternates between favorable and hostile conditions. Researchers are investigating whether these brief periods of moderate temperatures could support life, even if the overall conditions are harsh. A planet that spends part of its orbit in a temperature range that allows for liquid water may offer short-lived windows of habitability despite long periods of extreme conditions. This is akin to a region that alternates between a warm summer and a harsh winter where life must adapt to rapidly changing conditions. Injection recovery tests involve adding simulated planetary signals to real observational data and then attempting to recover them. This process helps scientists determine the sensitivity of their instruments and defines the detection limits for planets of various sizes and orbital periods. By inserting thousands of artificial signals into a dataset, researchers can map out the minimum planet mass and orbital period that their methods can reliably detect. It is like burying objects of various sizes in the sand and using a metal detector to see which ones it can pick up, thereby establishing the detector's performance. Direct imaging captures the faint light from exoplanets, isolating it from the overwhelming glare of their host stars. This method allows astronomers to study a planet's atmospheric composition by analyzing its spectral fingerprints for molecules like water, oxygen, or methane. Future telescopes may directly image a super-Earth and analyze its atmosphere to assess its potential for supporting life. Direct imaging is similar to using a powerful zoom lens with a glare-reducing filter to spot a tiny, dim firefly next to a bright lamp. Extended monitoring of stars over many years is crucial for understanding the full complexity of planetary systems. Long-term observations reveal both short-period and long-period planets and help track the evolution of stellar activity, enabling scientists to build accurate models of a system's dynamics. A 20-year study of a bright star might uncover multiple planets with different orbital periods, providing a comprehensive view of the system's architecture. It is like watching a slow map movie where every frame contributes to the full narrative, capturing details that short-term observations might miss. These advanced techniques, from high-precision radial velocity measurements and state-of-the-art spectrographs to sophisticated data modeling and long-term observations, are revolutionizing our understanding of distant worlds. By continuously refining our methods, scientists are steadily unveiling the secrets of exoplanets and expanding our knowledge of where life might exist in the universe. Published in Astronomy and Astrophysics, scientists have reported the discovery of a super-Earth with a highly eccentric orbit, a path that takes the planet on a wild journey between extreme temperatures. Unlike most planets that follow nearly circular trajectories, this planet's orbit is stretched out so that it periodically swings very close to its star and then recedes much farther away. How can such dramatic variations in distance affect its climate? And could life possibly survive under these conditions? When the planet is near its star, it experiences intense heating, potentially boiling off any surface water. Conversely, when it swings far away, the environment could plunge into deep freeze, causing water to solidify. Yet, intriguingly, the planet spends part of its orbit within the so-called habitable zone, the region around a star where temperatures might allow for liquid water. Could an atmosphere or other environmental factors moderate these extremes enough to allow life to persist, even if only intermittently? To understand this better, consider the physics involved. The concept of the habitable zone is based on the balance between stellar radiation and planetary cooling. In a circular orbit, a planet remains at a relatively constant distance from its star, maintaining steady conditions. However, in an eccentric orbit, the intensity of stellar radiation varies dramatically. Scientists use models that include the planet's albedo, atmospheric composition, and potential greenhouse effects to predict whether conditions could ever be stable enough for life. What if the planet has a thick atmosphere that acts like a thermal blanket? Such an atmosphere might redistribute heat from the star-facing side to the cooler regions, smoothing out the temperature extremes. Imagine a roller coaster that not only varies in speed and altitude, but also has a sophisticated climate control system inside. At the highest points, the ride is cold and slow. At the lowest, it is fast and heated. Now picture that the roller coaster car has built-in heaters and coolers that keep the interior temperature within a comfortable range, regardless of the outside conditions. Similarly, even though this super-Earth experiences severe swings from conditions akin to a scorching desert to those of a frozen wasteland, an effective atmospheric system could keep parts of the surface within a range tolerable for life. Scientists also ask, could transient periods within the habitable zone be enough to kickstart or sustain biological processes? On Earth, life has adapted to extreme environments, such as deep-sea hydrothermal vents or seasonal deserts. For example, certain microorganisms can survive rapid temperature fluctuations and even enter dormant states during harsh periods. Could similar adaptations occur on a planet that only occasionally enjoys temperate conditions? Another way to look at it is by comparing the planet to a house with an advanced climate control system. Even if the weather outside swings wildly from a blistering summer to a freezing winter, the house remains livable due to an efficient heating and cooling system. In this analogy, the planet's atmosphere would serve as the climate control system, potentially stabilizing surface conditions long enough for liquid water to exist during part of the orbit. Moreover, additional scientific models suggest that energy received during the brief passages through the habitable zone might trigger temporary warming events, melting ice or sublimating frozen volatiles, and creating short-lived environments where life could emerge or persist. Could these fleeting periods be enough to allow life to begin? Or might life evolve to take advantage of these temporary oases? Scientists continue to explore questions such as how the planet's rotation rate, axial tilt, and atmospheric dynamics might interact with its eccentric orbit. For example, if the planet rotates quickly, its atmosphere could circulate heat more efficiently, reducing temperature extremes. Conversely, a slower rotation might result in prolonged days and nights, exacerbating the heating and cooling cycles. Each of these factors adds another layer of complexity to our understanding of planetary climates. This discovery not only challenges traditional views of the habitable zone, but also opens up new avenues of research. It reminds us that nature is often more diverse than our models predict, and even worlds that seem inhospitable at first glance might harbor niches where life could exist. As scientists continue to gather more data and refine their models, they are asking deeper questions. Under what conditions can life adapt to such an unpredictable environment? And what does this mean for our search for life beyond our solar system? In summary, this super-Earth's eccentric orbit raises compelling questions about how life might endure in fluctuating environments. By considering factors like atmospheric heat redistribution, rapid adaptation, and transient habitable periods, scientists are expanding our understanding of where and how life could exist in the cosmos, all based on insights published in Astronomy and Astrophysics.